Okay, hello everyone. So let me turn my pointer on. Okay, so we're going to ray tracing in GRIN lenses. So right now there are two methods, finite ray tracing and ABC matrix product. Our goal is to unify two of the main models that are used, which is the shell and the slab. So in the shell model, you have a GRIN lens that is made up of many shells or layers like an onion. I can hear echoes. Does anyone have their sound on? Okay, it's not there anymore. And then the slab is, I'll hear it again. Okay, I'll just continue. So we unify both in the continuous limit. Where the shell is very, very tiny, then we can make a differential. Yeah, and then we will do paraxial retracing with the matrix. Yeah, to find the cardinal points and also the lens power. So how do we formulate the ray transfer matrix? We first look at the lens geometry. So we take the external parameters. So the front or the interior, length, radius, and conic constant, and the posterior radius and curvature. Yeah. We also have the anterior thickness and the posterior thickness of the lens. And then we have the refractive indices. And NOT would be for the aqueous and the vitreous humor, and S for the surface of the lens, and MC for the center of the lens. Then the inside geometry is determined by these external factors. So it's R and Q that determines the shape of the lens inside, together with the gradient index. Sorry, with the gradient parameter. So how do we formulate this ray transfer matrix? We go from the back to the front. Yeah. So here S is for the surface, for the posterior surface refraction matrix, and SA is for the interior surface refraction matrix. So we multiply matrices from the back to the front. So we have refraction, translation, refraction, translation, refraction, up to the last refraction at the interior. So that's how you multiply the matrices in matrix optics. So you have them here. Yeah, so we're going to call M GRIN, the GRIN matrix, all the translations and refractions going on inside of the lens through the different layers. And then we'll multiply that matrix by SP and SA to find the whole matrix of the lens. So I try to simplify the math for you. So here we start with this LK. This LK is just a product of a translation and a refraction. Yeah. So delta N is the index difference between the previous and the between the previous and the next layer. And that's the index to the right, and with a minus is the index to the left. Yes, this is the simple translation times refraction matrix. Then we multiply all of them. And depending on K, so K is the number of the layers that we give to our eye, to our lens. Yeah, so we multiply all those, do some magic, some approximations, and we arrive at this matrix over here, which is 1 negative thickness of the lens. And here we have 1 plus log of N naught over NT, which in our case, as you can see, here we have the same index on back and front surfaces. Yeah, so this log would be log of 1 is 0. So it would be 1 minus T, 1 here, and element 2, 2. And element 2, 1 would be this integral right here. Yeah. If you compare this with the matrix for a homogeneous lens, the only difference between them is, so this 1 minus T, 1, and this integral. So the only difference is in this element here, element 2, 1. And that will be the matrix of a homogeneous lens. Yeah, so we see the difference between the transfer matrix for a homogeneous lens and our GRIN lens, and the formulation that we have is this little integral right here, which is not, it depends on what model you take. It's going to be an easier or harder to solve integral. Yeah. So I just want to, I'll come back to this later. Okay, again. So I'm going to try to apply this formulation to two models. So I'm going to start with the GRIN 2 model because I work with Rafael Navarro here. So we first do this. We first apply that matrix formulation to this model. This is what we get with this model, which is a gradient parameter that changes the curvature. So besides the gradient index, there's also a gradient curvature radius. So these surfaces can change in shape. Yeah, from the outside in, the curvature radius and the axis changes. These are examples from, these are ex vivo lenses, and I don't recall right now where these were taken from. So the properties of this model is there's both a gradient refractive index and also a gradient curvature. There's a parameter G for the gradient, and the inner structure adapts to the external Q's and R's. And then this, you see this blue line right here is the intersection of all the isoindividual surfaces. So each color of these is associated with the same index inside of the lens. So where those intersect, we form the interface. Yeah. Here is this black solid line shows the index in the axis. Yeah. So this is the axis index. From the outside in, this will be the anterior surface. That will be the posterior surface, and that will be where we determine the thickness of the anterior and posterior to be. Yeah, so this is where in the axis, this is the anterior side and that's the posterior. Yeah, so this is shown for different G parameters. The blue would be negative 0.5 and orange, so increasing from negative 0.5 up to 2.5 with these colors. Yeah, and those are dp/dz. So the derivative of the power and the axis. Yeah, as we go along. So to test this model, we compared the direct matrix product. So I'm talking about, I'm going to go back here. Oh no, I went to here. So we're comparing this matrix product with n repetitions or n layers to the power that we obtain directly from just this integral. Yeah, adding it to the homogeneous lens power. Yeah. So we see that the matrix product is this red line. With 100 repetitions, we're still 2% away from the final value or best value. With 1,000, still 0.26, and with around roughly, I think it was like 8,000, we got a 0.03 to the final value. With our numerical integration, with that integral, we already get a 0.01% with 100 iterations, or 110, or was that 120? So I think we agree that it's a pretty fast way or an efficient to calculate power. Then we also found an analytical solution for our formulation, for the GRIN Q formulation. And it's useful because it's in terms of second-degree Gaussian and hypergeometrics, and these are both available in free and licensed products. Yeah, so it's this part here. If you look at this, this is n surface. Dn is the difference between the surface and the center, and this is the index at the center, and this is just constants: interior radius, the key parameter, the interior curvature, and the interior thickness. So this will be the equation for the power of the interior part, and this is the power for the posterior region. And these two F1s are the hypergeometric functions, which are programmed again into these two. Then we also compare with different approaches. Yeah. So we have an analytical, which is this, the numerical, which is the green dashed line, matrix product, which is multiplying all the LK matrices I showed you before, the slab model, and then the thin lens approximation. So what we found is we studied both the dependence on Q with the constant G and dependence on G with the constant Q. Yeah, so there's those two parameters. We made QP to be QA plus 1. So depending on Q, why isn't it going further? Sorry, there we go. The thin lens approximation is roughly 0.6 diopters above what we got for numerical, matrix, and analytical solutions. The slab approach is roughly 0.4 average below what we got for analytical, numerical, and matrix product. It's a little bit closer for very low Q or for high G. Yeah, you see there's a little bit more difference over there, but that was the average. And then between the matrix product and the direct trapezoidal or the numerical integration, we got a 0.06 diopter, like a 0.2% difference. We also wanted to apply this to different models. So we applied to the Avicano model, 2016, and this is the graph that appears on their paper. Yeah, these are the values of m. They use a parameter m in their formulation. If you want to know exactly what it is, you can just go to their article, 2016. It's easy to find. So this is the power in terms of the m value, which is a power in their equations. Yeah. So these are the lines that they find, and this is ours. Yeah, so we repeated with their formulation, we put their equations into, I should have put it there, sorry guys, into here. Yeah, so we put, it's just, as long as you have the n, how the index changes in the length and the curvature radius, you can find the derivative and find this integral. Yeah, so using that integral with their model, there we go. We got these lines. Yeah. So they actually have two parameters, the m and the p. So p 2.5, 3.0, 3.5, and 4. We use it's the same ones they used here, and then they have their value of m right here. So they look pretty similar, but how can you know? We don't have the real data, but I did try to squish and make the markers match. So just make this 0.2 match with that 0.2 and make this 25 with that 25. You know what I'm doing, like squishing the image on the right so it fits the same axis. Yeah, so it fits the axis on the left. So what I got is this. So I think it's a pretty good match. And I'm starting to think that this formulation can be applied to different models besides ours. So the conclusion of this, the main theoretical result is that the matrix for a GRIN lens is equal to that of a homogeneous lens plus the contribution due to the GRIN structure. Yeah, so the power, so this term is where you find the power. You multiply this term by n naught to find the power. So the power is the same of that of a homogeneous lens plus the contribution of the GRIN structure. And then in how it applies to the crystalline lens, we found the analytical approximation for Navarro's model, which is accurate and it's also computationally affordable. And we look at the impact of G and Q on the lens power. We're still looking more at that and how it affects, for example, accommodation and aging. So we're studying all of that now. And we think it's a general practical tool for actual ray tracing. And thank you for listening. That will be it.
Okay. Thank you very much, Veronica, for your